Jai Hind everyone. Today I am going to talk about the steady state error. What is steady state error, how it occurs, where it occurs, why it occurs, and how we can calculate the steady state error for any given system. So basically this steady state error is related with the time response of any system. Okay, what is time response? Time response is the response of the system with respect to time. Means how a system behaves when a standard test input signal is applied to it with respect to time. Okay, so basically there are two types of time response is divided into two parts. First one is the transient time response, and another one is the steady state response. So these two response define the time response of the system. Let's say, so this transient response is the initial part of the system, initial response of the system, right? And the post transient part is called as the steady state response of the system. So this transient response occurs in the transient state, while this steady state response will be achieved in the steady state. Okay, so whenever the response of the system passes as the time approaches infinity, we get the steady state and the corresponding steady state response of the system. Let's say I have applied the unit step input to any system. Okay, and I am getting this type of output for the system. I am drawing here second order system response for unit step input. This is basically for zeta less than 1, that is under damped system. Okay, you can see here that this is the initial part of the system which is called as the transient state. Here I am getting the transients in the initial part, right? And when the output tries to settle down with the passage of the time as time approaches towards infinity, this state is called as the steady state, right? And in the steady state only we will get the steady state error. You can see the deviation of output with respect to the input. You can see this will be the input and I am getting this output. So this deviation will be called as the steady state error. Okay, so we are getting the steady state error in the steady state. Okay, so the formula for the steady state error will be limit t tends to infinity et. We can get this formula from the final value theorem. Okay, in terms of frequency, the formula is limit s tends to 0 s into es, and we can define the steady state error as the deviation of the output of a control system from the desired response during the steady state is known as the steady state error, and it will be represented by ESS. So let me derive the value for the this error. This is the error which is generated after comparison of the reference input with the feedback from the output, right? Let's say this is not the unity feedback system. Let GS be the forward path gain, HS will be the feedback path gain, and let BS will be the signal from received from the HS. Okay, and this ES is here is the error signal, right? So I can write this error signal ES will be equal to RS minus BS. Okay, also I can write this value of BS CS into HS. Okay, so let me put this value in the above equation. So I am getting ES which is equals to RS minus CS into HS. Okay, now you can see here that this CS will be equal to ES into GS. So I can write CS will be equal to ES into GS. Now if I'll put the value of CS in this above equation, I am getting ES will be equal to RS minus ES into GS into HS. Okay, so when I am shifting this ES part into the left side and take ES as common, I am getting 1 plus GSHS will be equal into ES will be equal to RS, and from here I am getting ES will be equal to Rs upon 1 plus GSHS. So this ES is the error signal here, right? So when I'll put the value of ES in this equation, I will get the value of steady state error as limit S tends to 0 S into Rs upon 1 plus Gs into Hs. So this is the value of the steady state error which is required, which will be calculated depending upon the value of Rs, depending upon the value of Gs and Hs. So since I have told you that time response is calculated whenever the standard input signals are applied to it, so I'll calculate the steady state error for different test inputs like step input, ramp input and the parabolic input. And related to this steady state error, there are static error coefficient. Basically there are three types of static error coefficient. One is the positional error coefficient. Okay, this is calculated only when unit step input is applied to any system, and it is represented by Kp. Another one is the velocity error coefficient. Okay, this is this can be calculated only when the standard when the step ramp signal is applied to any system, and it is represented by Kv. And the third one is the acceleration. This is acceleration error coefficient, and this is represented by Ka, and it is applied only for the system. It can be calculated only for the system in which the parabolic signal is applied. Okay, so one by one I am calculating the value of this static error coefficient along with the steady state error. So we know the formula for the steady state error, which is limit S tends to 0 S into Rs upon 1 plus GSHS. So when unit step input is applied to any system, the value of Rs will be 1 upon S, right? Laplace of unit step signal is 1 by S. So when I am putting this value in above formula, I am getting steady state error will be equal to limit S tends to 0 S into 1 by S upon 1 plus GS. Here I am taking the unity feedback system. So Hs here is equals to 1 for this system. If it is not, then I can put the value Gs into Hs here. So when this get cancelled, and here the steady state error will be 1 upon limit S tends to 0 1 plus Gs, and let this limit S tends to 0 1 plus Gs will be equal to Kp. So the steady state error will be 1 upon, sorry, this one is not required here. Sorry. Let this, I can write the value directly. So only this limit goes with this S term, no? This is the constant. So I can write it 1 upon 1 plus limit S tends to 0 into Gs. And now let this limit S tends to 0 into Gs will be equal to Kp. Okay. So the steady state error will be 1 upon 1 plus Kp for the system in which we have applied the unit step signal. Okay, and the value of Kp will be limit S tends to 0 into Gs. Similarly, I can find out the value of velocity error coefficient, that is Kv, for the unit ramp input. So Rs for the unit ramp input will be 1 upon S square. If I'll put the value of Rs in the above equation, we'll get limit S tends to 0 1 upon S square. This gets cancelled here, and this is 1 plus Gs. So I can write it like 1 upon limit S tends to 0, here S plus S into Gs, Okay. Now when this limit is applied here, so it becomes 0. So this is 1 upon 0 plus limit s tends to 0 s into gs. See, here it is again for the unity feedback system. That means value of hs here is again 1. So let this limit s tends to 0 into s into gs will be equal to kV. Okay. So we will get the value of steady state error as 1 upon kV. So the value of velocity error coefficient will be limit s tends to 0 s into gs, and the corresponding steady state error will be 1 upon kV. Now the third one is the acceleration error coefficient, that is ka, and it is applied only to those systems, and we can also calculate ka only for those systems in which the input is static parabolic input, right? So the Laplace of unit parabolic input, the Laplace of unit parabolic input will be 1 upon s cube. So when I am putting the value of rs in the above equation, I am getting limit s tends to 0 s into 1 upon s cube upon 1 plus gs. Okay, here again hs is equals to 1. So I can cancel out this and I can write limit s tends to 0 s square plus s square into gs. So this term directly gets 0 when I put the limit here, and I am getting 1 upon 0 plus limit s tends to 0 s square into gs. So let ka will be equal to limit s tends to 0 into s square into gs. Okay. So the steady state error for the system when unit parabolic input is applied to it will be 1 by ka, and the ka is the acceleration error coefficient, and the value of ka will be equal to limit s tends to 0 s square into gs. And this is for the unity feedback system. If I am having non-unity feedback system, then this get multiplied with hs as well. Okay, so this will be the value of ka in that case. So this is the summary. So these are the error constant kp, kv and ka. Value will be limit s tends to 0 into gs, right? And it is applied only to the signal when input is to the system, only when the input signal is step signal, right? And the corresponding steady state error will be 1 upon 1 plus kp. And the another one is the velocity error coefficient will be applied to signals systems which are having unit ramp as the input, and the value of this velocity error constant will be limit s tends to 0 s into gs. Corresponding steady state error will be 1 by kv. And the acceleration error constant value will be limit s tends to 0 s square into gs, right? And will be applied to the systems which are having unit parabolic signal as the input, and the corresponding steady state error will be 1 upon ka. Please note that the impulse signal, for the impulse signal, steady state error cannot be calculated it is applied to a particular point. Okay. Now coming to the type of the system, how we can calculate the steady state error and static coefficients for any system which are depending upon the type of the system, right? So let us consider this system, unity feedback system, which is having open loop transfer gain gs will be equal to k into 1 plus ta into s into 1 plus tb into s into 1 plus tc into s up to so on till 1 plus tm into s, right? Denominator may we have s raised to the power n, okay, into 1 plus t1 into s into 1 plus t2 into s till so on. At the end we have 1 plus tp into s. So what is the type of system? The type of the system will be defined as the pure integrators in the forward path of any unity feedback system, right? So this type of the system will be equal to n. This n will define the type of the system. For example, if value of n is 0, that means we have s raised to the power 0. So this is the type 0 system. If value of n is 1, then there is one pole at origin and the type of the system will be type 1. If S value of n is 2, that defines the 2 poles at origin, and this is the type 2 system. So this S raised to the power n will represent the pole of multiplicity n at the origin. Depending upon this, we can call type 0 system, type 1 and type 2 up to so on. See, as the type of the system is increased, the accuracy of the system will also improved, right? So for these 3 type of the system, type 0, type 1 and type 2, we will calculate the static error coefficient and the corresponding steady state error. So starting with the type 0 system, let us take GS is equals to K into 1 plus Tz1 into S, 1 plus Tz2 into S up to so on upon 1 plus Tp1 into S, 1 plus Tp2 into S. Okay, you can say that this is the type 0 system. Since here S raised to the power 0, which is equals to 1. Okay, so this is the type 0 system. For this type of the system, let's find out the value of Kp, Kv and Ka. Since we know that if we want to find out the value of Kp, the input Rs will be equal to 1 by S. That is unit step input, right? Now here GS is given to us, okay? And the value of Kp we know, limit S tends to 0 into GS. So let's put the value of GS in this equation to find out the value of Kp. So this is limit S tends to 0 and this is K into 1 plus Tz1 into S into 1 plus Tz2 into S up to so on upon 1 plus Tp1 into S into 1 plus Tp2 into S up to so on. Okay, so when I am putting the value of S which is equals to 0 here in this equation, all of the places I am getting Kp is equals to K, right? And the corresponding steady state error now will be, ESS will be, we know 1 upon 1 plus Kp hoti hai value. So I can write the value here, ESS will be for this system 1 upon 1 plus K. So for type 0 system, the value of Kp will be K, that is the constant, and steady state error will be 1 upon 1 plus K. Now if the unit ramp input is applied, so we will have the value, we can find out the value of Kv, which is limit S tends to 0 S into GS. Okay, S into GS. Now putting the value in this equation, limit S tends to 0 and the value of GS here is K into 1 plus Tz1 into S, 1 plus Tz2 into S up to so on, okay, upon S raised to the power 0 means 1, okay, 1 plus Tp1 into S, 1 plus Tp2 into S up to so on. So when I am putting the value of S here 0, okay, and we are having also now S here, okay, S into this is GS. So this S is equals to S raised to the power 0 means 1. So here when I am putting the value here 0, that means S into K, that means value of Kv here will be 0. So the value of Kv here will be 0. Corresponding steady state error will come to be infinite. Okay. So for type 0 system, the velocity error coefficient will be 0 and will get infinite steady state error. Now let me calculate the value of Ka, okay, acceleration error coefficient. The formula for the Ka will be limit S tends to 0, that is S square into GS. Now put the value of GS in this equation. So this is S tends to 0, S square into GS. What is GS? K into 1 plus Tz1 into S, 1 plus Tz2 into S up to so on. ठीक है, upon 1 plus Tp1 into S, 1 plus Tp2 into S up to so on. right? So you can see here directly if these quantities are also become 0 due to this limit, but there we are having a multiple of s square. So again here Ka will become 0 and the corresponding steady state error will be 1 upon Ka again, which is infinite. So for type 0 system only we can find out the value of Kp, which is 1 upon 1 plus any constant, that is K, and the corresponding the value of Kp के साथ we can find out the value of steady state error. And for velocity error coefficient and static error coefficient, the corresponding steady state error will be infinite. Now coming to the type 1 system. So when we are having one pole at origin, that means s raised to the power 1. So this will be called as the type 1 system. Okay, there is one pole at origin. Now let's again find out the value of Kp, Kv and Ka and corresponding steady state error for type 1 system. So for type 1, Kp again here will be limit s tends to 0 into Gs into Hs. Here Hs is 1, so I am directly writing the value of Gs. So put the value of Gs in this equation. I am getting limit s tends to 0 and Gs here is K into 1 plus Tz1 into S, 1 plus Tz2 into S up to so on upon, here we are having S 1 plus Tp1 into S, 1 plus Tp2 into S up to so on, right? So when I am putting the limit s tends to 0 in this equation, here this becomes 0, this becomes 0, okay, denominator again all these quantities become 0, but here we are having the s in the denominator, due to which the value of Kp will become 1 upon 0 means infinite, and the corresponding steady state error, the formula is 1 upon 1 plus Kp. So when I am adding something to infinite, it will become infinite, and something upon infinity will be equal to 0. So for type 1 system, the value of positional error coefficient will be infinite and the corresponding steady state error will be 0 here, right? Now let me calculate the value of Kv. So value of Kv here is limit s tends to 0 s into Gs. Put the value of Gs in this equation. What I am getting is Ka. This is Kv, sorry. This is Kv, na? Limit s tends to 0 and s into Gs is K into 1 plus Tz1 into S, 1 plus Tz2 into S up to so on, okay, upon S into 1 plus Tp1 into S, 1 plus Tp2 into S up to so on. Okay, so again here this S gets cancelled with this S and all these values which are having term S will become 0. So what is the value of Kp? It will be equal to K. So the corresponding steady state error will be 1 upon Kv, which is equals to 1 by K. So we are getting the value of velocity error coefficient in this case for the type 1 system, and corresponding steady state error will be some constant. Okay. Similarly, I can calculate Ka, which is limit s tends to 0 s square into Gs. Now putting the value of s square here, Gs here, I am getting s square into, this is K into 1 plus Tz1 into S, 1 plus Tz2 into S up to so on, okay, upon 1, here what is this? S, okay, and this is 1 plus Tp1 into S, 1 plus Tp2 into S up to so on. So this न्यूमरेटर में s की पावर 1 से s डिनोमिनेटर में कैंसिल आउट हो गया, स्टिल आई एम गेटिंग s in the numerator. So the value of Ka after putting limit s tends to 0 will be 0. Okay, so the corresponding steady state error again 1 upon Ka will be infinite for the acceleration error coefficient. Okay. Now coming to the type 2 system. See here the value of S, see here there are two poles at origin, that means we are having S square. So this defines the type of the system, which is type 2. Again here I am calculating the value of Kp, Kv and Ka for type 2 system. So what is Kp? Kp here is limit S tends to 0 into Gs. Okay. So put the value of Gs in this equation, limit S tends to 0, K into 1 plus Tz1 into S, 1 plus Tz2 into S, up to so on, upon, here we are having S square in the denominator, because of which the value of Kp will become infinite. Okay. And corresponding steady state error again will become 1 upon 1 plus infinity means 0. Right. Now Kv, here limit S tends to 0, S into Gs. Putting value of Gs again here, then it will become infinite, because I am having S square in the denominator. One S will get cancelled with the numerator, but the other will remain. The one S raised to the power 1 remain here, because of which I am getting the value of Kv, one power get cancelled here. Again the value of Kv will become something upon 0 is infinite, and the steady state error for 1 upon infinity means 0 for type 2 system. Now Ka will be limit S tends to 0, S square into Gs. Now here when I am putting the value of Gs in this equation, that means K into 1 plus Tp, this is Tz1 into S, 1 plus Tz2 into S, up to so on, upon 1 plus Tp1 into S, 1 plus Tp2 into S, up to so on. Here I am having S square also. So it S square now gets cancelled, and the value of Ka will be equal to K. So the corresponding steady state error, since Ka is equals to K, so the corresponding steady state error will be equal to 1 upon K. So this is the summary for different type of inputs and for the different type of system. For type 0 system, right, when a step input is applied, we have the steady state formula, error formula is 1 upon 1 plus Kp. So the static error coefficient will come out to be some constant, and the error will be 1 upon 1 plus Kp. But if ramp input is applied for type 0 system, then the velocity error coefficient will become 0 and the steady state error will be infinite in that case. And for parabolic input, the acceleration error again coefficient will again become 0 and the steady state error will become infinite. And for type 1 system, when step input is applied, then the value of Kp will be infinite and corresponding steady state error will become 0. For ramp input, the Kv will be some constant value, will get some constant value of Kv, and corresponding steady state error will be find out, that is 1 upon Kv. Okay. But for parabolic input here, again I am getting the value of Ka as 0 and the infinite steady state error for the parabolic input. But for type 2 system, I am getting the value of Kp and Kv as infinite. So the corresponding state error will be 0 and the value of Ka is some constant, and the steady state error will become 1 upon Ka. So from here you can observe, as the type of the system is increasing, just see the steady state error in all the cases. As the type of the system is increasing, we are getting the improved the improved system. That means the error is reducing to the 0, and here we are getting some constant value, while here the error is infinite in case of type 0 system with some constant value, and also here धीरे धीरे it is improving, या 0 मिली, कुछ constant मिली, but infinite मिल रही है. But here in type 2 system हमने कुछ भी input applied किया, either the constant value is obtained or the 0 error is obtained. Okay, so as the type of the system is improving, then the error is improved. That means we are getting the reduced error for any input. Now there are some numericals that I want to discuss related to these error coefficient. Since derivation we have done in the previous slides, so I hope you can easily solve these numericals. These are very simple numericals which are related to the steady state error, right? Value of GS is given to us, and I have to find out here the velocity error coefficient, position error coefficient, and the acceleration error coefficient along with the steady state error, right? Since we know the formula for Kp is limit s tends to 0 into GS. So simply I have to put down the value of GS in this equation, and now putting the limit. So this is s into s square plus 2 zeta omega n s, plus you can directly solve by putting the limit here, or you can see that this is the type 1 system. For type 1 system we are getting the value of that Kp as infinite. If I put here well limit s tends to 0 in this equation, then what will be the value of Kp? It is infinite. Okay, so the corresponding steady state error will be 0 in this case. This is type 1 system. Okay, and again Kv, I am doing first part here. This is the first part now. I am doing first part. For the first part, for Kv here the value is limit s tends to 0 s into GS. Okay, so I can put the value of, do I have another, s into GS की वैल्यू क्या है यहाँ पर हमारे पास, k upon s into s square plus 2 zeta omega n into s plus omega n square, right? When I am putting the value of s here, the s gets cancel and this will become 0, this will become 0, and what is the value now? K upon omega n square. So for type 1 system I am getting some constant, that is k upon omega n square, right? So the value correspondingly steady state error will be 1 upon Kv. So what is this? It will become omega n square upon k. Okay. Similarly, you can calculate the value of Ka. Okay. Here, so Ka will be equal to limit s tends to 0 s square into GS. So when you are putting the value of GS in this equation, that is limit s tends to 0 s square into k upon, this is s into s square plus 2 zeta omega ns plus omega n square, then you will you can cancel only 1, so 1 power of s, so Ka will become here 0, and correspondingly steady state error will become 1 upon 0 equals to infinite. ठीक है. Similarly second part can be solved. Okay, you can solve second part by yourself. Now this is another question here. I have to find out the value of K when the steady state error is around 10% given to us. Okay, since we know this is the type 1 system. Okay, so from type 1 system we can find out the value of Kv, velocity error coefficient for ramp input, right? So we know Kv is limit s tends to 0 and this is GS, s into GS, right? So I can calculate the value of Kv from here, and steady state error is also given to me. Then by comparing I will get the value of K. So you can see here limit s tends to 0 s into k into s plus 5, right, upon s into s plus 6, s plus 7 and s plus 8. Okay, so what is this, s gets cancelled here, and putting the limits, what I am getting the value of Kv will be equal to k 5k upon 6 into 7 into 8. So it is 56 into 6. Okay, 336. So this is 5k by 336. Okay, and also we know the steady state error, which is here 0.1 given to me. Okay, and steady state error, value of steady state error is 10%. 10% means 0.1 na, sorry, 10 upon 100. So it will like then 0.1 ही आएगा, and 10% means kV, 1 upon kV in this case, right? So kV from here, what is the value of kV from here? That is 0.1. So by comparing the value of kV from this and this, we will get the value of k, which is 5k upon 336, comparing equation 1 and 2. Okay, this is given to me. So from here I calculate the value of k, which is equals to 672. So that's all for today's lecture. Thank you so much.